It's a great pleasure to introduce Professor Peter Clarkson. Peter is Professor of Mathematics at the University of Kent, and many of you, I'm sure, know him and his work very well. So Peter is an expert in theory of integrable systems, special functions, nonlinear special functions, Pauli equations, Pauli transcendence, and orthogonal polynomials. Many things, and today he will give us a general introduction in overview of the connection between many aspects where special functions or orthogonal polynomials come up in across from theory of matrix models to the orthogonal polynomials. Okay, so a big pleasure.
Thank you. Thank you, Antonio, and thank you to Antonio and the organizers for this opportunity to give a talk here. It's rather appropriate I should actually give this talk in Northumbria because when Marta Galati visited Kent a couple of years ago, she made a chance remark, and that led on to me finding out about the work that Constanza, Antonio, and Marta had done. And as you see, that's been a big motivation for some of the things that I'm going to report on today. So this motivation dates back to a paper by Jurkovic in 1991, in which he was looking at a matrix model, as you'll see shortly. And the title of the paper is Chaotic Behavior in One Matrix Model. And these are reproductions of two of the figures that appeared in his talk. In his paper. More recently, the work done in Northumbria, we visited the work of Djokovic and interpreted these as a dispersive shock. And these are two of the figures taken from the paper by Benanzi and Mora that I've reproduced. So, let's give an outline. I'm going to first give an introduction, and then, because I'm interested in orthogonal polynomials, I'm going to go to a slightly simpler case first of taking this quartic Freud weight. And then I'll move on to the main part, which is looking at various sextic Freud weights. And then in the end, we'll move to this case here at the end, where I'm going to compare these two weights, which is sextic equivalent. The second weight is the one that arises in matrix models. The first rate is something that you more find if you look at orthogonal polynomials. So that's going to be the outline of what I'm going to do. Now, I'm not an expert in Hermitian random matrix models, but I'll just give you a brief overview to show the link between this and orthogonal polynomials. So in the study of Hermitian random matrices, one of the important aspects is the so-called partition function, which is just a multiple integral as given here, where you've got over the trace of Hermitian matrices, and it's over a span of n by n Hermitian matrices. Now, it's well known that you can rewrite this partition function as a multiple integral that involves the eigenvalues of the matrix, and this is the form that you have here. And so these are equivalent. Now, in general, you just take in a polynomial. In this case, I'm going to take the polynomial to be symmetric and of degree 6. So if you look to a symmetric monic orthogonal polynomials, then the polynomials satisfy this orthogonality condition. I'm writing this on the real line. So it doesn't have to be necessarily on the real line or the whole real line, but in the cases I'm going to look at, we are going to be on the whole real line. And one of the important aspects of orthogonal polynomials is that they satisfy a three-term recurrence relation. And you can explicitly get what the recurrence coefficients are in terms of the polynomials themselves. Now, I'm interested in symmetric weights. And so therefore, the coefficient an is necessarily an odd integral, so therefore it's 0. And so I'm just looking at a simple three-term constellation. That's one recurrence coefficient, the beta n, and it's that I'm trying to evaluate. So now we can explicitly write what this recurrence coefficient is in terms of these Hankel determinants, which are made up of the moments, which is just the integrals of x to the k times the weight. So knowing the weight, you can work out the moments. From moments, we can get the Hankel determinants, and from there we can work out the recurrence coefficients. Now for symmetric weights, all the odd moments are 0. And further properties are that the Hankel determinant has this integral representation, which is essentially just the partition function derived from random matrix. And we can also write the coefficient Hn, which is what happens when you take the integral of the Pn squared times the weight in terms of these Hankel determinants. Now, because we're in a symmetric case, things are slightly simpler in that half the elements in the Hankel determinant are 0, and so we can rewrite the recurrence coefficients beta n in terms of two smaller determinants, what I'm calling an and bn, and you notice there are two different representations whether beta n is even or odd. Furthermore, if, as is the case here, the weight is of this particular form, and I'm assuming that all the moments are going to exist, otherwise pointless exercise, then we can actually write the functions an and bn as Wronskians just purely of the lowest order simple mu naught. So you can actually do that. So you only need to then work out mu naught, and then you just write Wronskians to work out the rest. Now, one of the things about the Freud weight is it's called a semi-classical orthogonal polynomial. And it's related to the so-called Pearson equation, referring to the top there, where omega is the weight. And then there are two polynomials, sigma of x and theta of x. Now, for classical orthogonal polynomial, such as Hermitian, Laguerre, Jacobi, then the degree of sigma is less or equal to 2, and degree of theta is equal to 1. For semi-classical, it's determined that one of these two doesn't hold. And so here are three examples of semi-classical orthogonal polynomials, where in each case the theta is a degree more than 1. There's also another aspect to it in that for the classical orthogonal polynomials, the sigma and the theta are the coefficients in the differential equation satisfied by the orthogonal polynomial. It's not the case here. The differential equations are far more complicated. You can derive them, but they're far more complicated. Now, I'm interested in Freud weights, and they've been known for almost a century. The relationship between the Freud weights and integrable systems dates back to first to the work of Shohat, and then to Freud in 1976. And whilst various discrete equations were derived, it wasn't until Fokas and Kitaev in 1991 identified them as discrete Pan-Lavey equations. Magnus in 95 considered this Freud weight here and wrote the coefficient in the three-term recurrence relation in terms of solutions of the fourth Pan-Lavey equation and the discrete and the string equation, this equation here, which is also known as discrete Pan-Lavey 1. And this had previously written in the string theory and also in orthogonal polynomial theory as well, in connection with this weight. Now, Freud was interested in the weights at the top here, and he derived discrete equations for the beta n in the cases m equals 1, 2, 3. If m equals 1, it's just an extension of the Hermitian polynomial. If m equals 2, this is just a special case of discrete panel of A1. And this is a higher order one we'll see is the second member, special case of the second member of the discrete panel of A1 hierarchy. And Freud also made a conjecture in the general case as to what happens to beta n as n gets large. So now let me look at this generalized quartic Freud weight. I'm doing this one because it's a simpler one to discuss. We can get things explicitly very simply. So in this case, I just need to work out mu naught. And it turns out I can just divide this as an integral, realize what the integral is as an integral representation of a parabolic cylinder function. And so I explicitly get what mu naught is in terms of parabolic cylinder functions. I can work at all the mu2k as derivatives of mu naught. All the odd ones are 0. And that's if rho is not an integer, or not two. If it's of the form 2n plus 1, I can write it out in terms of error functions. So everything is explicitly known. You can then write down what the recurrence relations actually are, explicitly in terms of this mu naught, which is in terms of the parabolic cylinder function. And you can actually show that the logarithm derivative of A naught, of AN, satisfies this second order, second degree differential equation, which in the integral world is known as sigma 4, the second order, second degree differential equation associated with the fourth panel of A equation. So here's explicitly what it is in terms of panel of A4. You got different results, whether they're even or odd. So we know that the beta n satisfies the differential equation and is a difference equation, and these two are related by the Backen transformation of panel of A4. In the Backen transformation, if you eliminate the derivative, you get the discrete equation. If you eliminate the discrete motion, then you actually get the differential equation.
I think that the slides are frozen on Zoom. So usually, just unshare and share again. Unshare.
Thank you.
Okay, yeah, okay, thank you.
Okay, so now I want to look at this. Look at the discrete equation, the solution to the discrete equation. So if I assume that beta 2n is u and beta 2n plus 1 is v, I can just get a simple system here. If rho equals 0, I can explicitly solve it. If rho is not equal to 0, I can find quartic equations for u and v. And if you plot them, then what you find is that in the red I've plotted the first one here, the blue and black, and you see the even ones follow the blue line almost perfectly, and then they jump onto the black line. And the odd ones follow the red line, and then move on to the blue line of the black line almost perfectly. There's just this transition region in here, but they almost exactly follow those lines perfectly. If you look at the case when a row is positive, then you can plot these quartics, and I plotted them in the first quadrants. And these are what the plots are. Now, if you put on top the solutions of the beta ends that I get, well, there's the quartic, and you can see they almost exactly follow it. So to the naked eye, they follow it. The difference is about 10 to the minus 4 when you actually calculate it. But to the naked eye, that's a pretty good approximation. You can't really tell. So now let's look onto these sextic Freud weights. So I've now changed the quartic term to a sextic one. Now here we have a certain problem. I don't have neutral representation to start with, but I can actually work out explicitly what this actually is in terms of three 1f2 functions, so three geometric functions. And the way to actually prove it is you assume you can interchange differentiation and integration. You can show that the mu naught satisfies this third order equation. And then we can solve that third order equation in terms of 1f2s. The advantage of working with people who are experts in geometric functions. And then I know what the initial conditions are, put those in, and I get the answer. So the 1f2 is a third order function. That's the differential equation it satisfies. And knowing that, you can do the same as I did in the quartic case and actually write down what all the beta ends are in terms of this AM, because I know what mu naught is. And I can go the same idea. And I'm going to take U to be beta 2n, V to be beta 2n plus 1. You can write down the system. If rho equals naught, you can do this trick of letting U equal eta minus xi minus eta and V xi plus eta, and then get two equations, a cubic for xi, and then you can get eta. If rho is non-zero, you can get these algebraic equations for U and V. And so we can do this whole same thing. I can do the plotting, and if actually the same sort of thing happens in this case as in the quartic case, that they follow the blue or the red line, depending on whether it's even or odd, and then they join up and follow the black line. The black line is just taken by assuming all the betas are the same. And that's if rho equals 0. If rho equals non-zero, then they do exactly like they did in the quartic case, and the even and odd follow the solutions of this almost exactly for all n. Again, the difference is very small. So now I'm going to put the two bits together. So I'm now going to include a quartic term here. What do we have? Well, you can work out the differential equation in the same way I did before. So just one problem. It's a third order linear equation. I can't solve it, except in two special cases. Now, I've been doing nonlinear equations for a long time. And I always thought the linear equations were trivial. Yeah. Just can't solve it. Except in these two cases. If rho equals 0 or t equals 0, I can solve it. It satisfies a linear PD. Now, how I tried to do it, I just can't solve that equation. I've even taken, I've also suggested I just take Laplace transforms. You just get down to an integral you can't do. You're no better off. So it really is a problem that you can't solve. We can derive the discrete equation, which is the general form of discrete parallel 1, the second member of the hierarchy. It satisfies two differential difference equations, and it satisfies a differential system. I can actually eliminate, say, beta n plus 1, well, then get a fourth order second degree differential equation, which is not going to help me. And also, I couldn't fit it on the slide if I wanted to. I'd never even bothered to work that. So now I'm going to move on to the case I'm really interested in. So I'm now going to drop the road. And now instead of having t, I'm going to replace t by kappa tau squared. You'll see in a minute why I'm doing that. Now, of course, now I'm excluding the case t equals naught or kappa equals naught. And I've already dealt with that before when I had this general sextic point. So I know what the answers are. And then I have these two equivalent weights where I have these different parameters. Now, first, I don't do the above weight. I'm going to do the analysis I can do. You can show that this weight now satisfies this third order linear equation. And we know the initial conditions. Now, in this case, we can actually solve it in three specific cases. Well, to date, we've solved it in three specific cases. Kappa equals a quarter, kappa equals a third, and kappa equals 0. And you can see in all those three cases, the differential equation simplifies considerably. And all the solutions we find are in terms of 2f2 type geometric functions, which again satisfy our third order equation, which I've given here. So let's first take kappa equal to quarter. Then this is the differential equation at the top. And these are the solutions in terms of 2f2s. You might say, well, isn't there a third solution because it's third order? The third solution is 0 because of the initial conditions. And this simplifies because I have 5/3, for example, in both places there, so it's a 1f1. And then because of this ratio of 2 to 1 here, I can solve that and replace that in terms of modified Bessel functions. So I've got the solution in terms of modified Bessel functions, and in fact, you can show that mu naught satisfies this second order equation. If kappa equals a third, we can solve it in terms of, again, 2f2 functions with different parameters at the top and a different here. And same for kappa equals 0. We can actually solve it in terms of 2f2 functions. Now, what about the mu2n? I can't use the Monsignor idea, so I have to do something different here. Now, it turns out you can write down a third order linear equation. And again, I can only solve it in three cases to date. The same three cases. And they're all expressed in terms of these three 2f2 functions. Both there's two secondary parameters, the b's, so are the same in all three cases. And these arise from the third order equation. The moments also have a discrete equation you can derive as well. So now, let's look at kappa equal to a quarter. And this is what the solution actually is. You can actually derive. We just solve the differential equation, and this is what it gives. You just have to put it into Maple, and it'll like tell you what the solution is. Now, the interesting thing is that you can actually express all of these in terms of modified Bessel functions. So you can actually write all of these mu2n for kappa equal to quarter in terms of modified Bessel functions. We could explicitly what the f, g, and h are. And right here are the first few, where I can actually write down and show that I can solve it in all the cases in terms of modified Bessel functions. If I look at the cases, capital equals to a third and 0, again, I can get them in terms of two functions. I've slightly modified the, in the case capital equals a third, because then I can write the weight in a slightly simpler way. So again, I can explicitly get all these down. So I can write down everything explicitly as well. Okay. So now let's go back to the previous work. So now I want to link this to this weight here. We need to see that these two weights are equivalent. Now, as I mentioned before, Djokovic in 1991 wrote a paper with this title, Chaotic Behavior in the One Matrix Model. And he chose this weight here with these particular parameters. Now, in terms of the weight at the top, this is the case of kappa equal to 1/3.
Sorry, Peter, just if you can clarify, so these choices of kappa equal to a fourth, a third, and 0, do they correspond to a particular form of the potential? So what is the...
Yes, they have multiple. I mean, perhaps I'm writing this right.
Yeah, you can.
A quarter is the exponential of minus x squared minus a half for all squared. A third is the exponential of minus x squared minus third to cubed. And 0 is the exponential of minus x to the 4 x squared minus 2. So yes, they are. Well, there is a constant at the end of it, but that doesn't matter. But there are three. You've certainly got multiple roots or multiple double roots. So yes, they are. And that's perhaps why we can solve it. So this is the numbers he chose, and I've just reproduced two of the figures he actually had, which I showed you earlier. The dashed line is what happens if you take the discrete equation that all the beta ends with a set. There was a work by Senechol in 1992, where he had his title was Chaos in the Hermitian One Matrix Model. And these are 4 pictures I've reproduced from his paper here. He had a slightly bigger n. And so there was ideas that this was looked like chaotic. And then the more recent work of Benazzi, Moro, and Galati. So they were also looking at this and explained it in terms of dispersive shock waves. So if you was the recurrence coefficient satisfy this discrete equation here. And so if you set beta n to be beta for all n, you get a cubic equation. And these are reproductions of the plots they had. So what we then did was I took those and effectively put dots on the top of all of these, which is what you've done. And that's what you get. And then what you start to see, certainly it's true in this particular case, you see that there's these lines. So we thought, why don't we color them in 3 different colors? And that's what we got. And so it's like a kind of sampling that they're following curves, but they've just been sampled. So that then equals 100. If you put n to be 250, then you just simply get more waves because you've got more points. So you actually, that's what you actually get. You get these, again, they appear to be these threes. Now, they only considering G6 above 0.005. And so if we then thought, well, what happens if we go below 0.0? And this is what you start to see. Again, they're committing threes. But noticeably, here you see they're starting in two lines here, whereas in this one, they're just starting at one line. So a subtle difference, or major difference we'll see. And if you increase the n to 250, then you just simply get more and more oscillations. See, no? And so we have this situation of comparing between the two different regimes, whether you have starting, it's what the even and the odds start with following different curves, or they start with the same curve. Now you should rightly be asking me what happens at 0.005. I'll come on to that. Okay. So we have this scenario. So we've seen that this is going to happen. So firstly, we have a polynomial involved. And we do expect that the roots of the polynomial are going to determine some of the behavior. It seems natural. And we can just look at the different cases, and you can see you've got very different cases depending on the multipliers of kappa and tau. This is one of the reasons we chose kappa, because it gave this classification much simpler. So you take the U here, this is what you get. So you can see that kappa to a quarter is a very special value. And for this, for the equivalent polynomial, the important property is G2, G6 over G4 squared. So we've got all these different cases to consider. Let's take the first case. I'm sorry, let's plot them so you can see that you've got different kinds of options for the polynomial U, depending on these different cases and how many roots they have. So, just maybe a word about the numerics of how I did these calculations. Well, they're all done numerically using Maple. And I'm using this discrete equation here. I'm taking the four initial conditions, beta naught, beta minus 1, beta naught, beta 1, beta 2. I work out beta 1 and beta 2 numerically using Maple. And then I use this recurrence relation to work out all the subsequent betas. Now, this is incredibly sensitive with regard to initial conditions. And so I have to use hundreds, if not thousands of digits in the calculations. Times I've gone up to about 3,000 digits. Fortunately, laptops are sufficiently powerful to do that. You have to do it in a simple manipulation. You can't use it couldn't do it in MATLAB. And you have to give all the initial data as fractions, not as decimals. You'll just simply won't, but you won't have the such accuracy. Okay, so now let's look at this one branch case. So if we set beta n to be beta, you get this cubic here. And you can see that the cubic has certain special cases. We're looking at the kappa bigger than a quarter, and you can see that when you get to 0.25 or 0.5, it's a gradient catastrophe. So you're going to get multiple solutions until you get to 0.4. And you can work out explicitly where values of n with these are. That's not difficult. And so, as we've seen, these are now put tau equal to 20 for various kappas here. We get these oscillations if I do it in threes. And you see as well that the range, where you got these this transition period shrinks as you increase kappa. So that's a kappa tau equal to 20. What happens if we increase kappa? What we consider is tau. So here I've now put tau. This is for kappa to 0.3, taking tau between 35 and 50. And you start to see now regions of sort of quasi-periodicity that is developed. It's all not the same periodicity, but different in different values of kappa. And so there's also, sorry, this is kappa the same, so it's just the different taux, they're just simply getting more intense. But I certainly say the number here is the same as the number in here as well. I think it's 11 in there, 11 there as well. But it's not 3, it's 11. You take kappa to third, again, as you increase tau, certainly for large, if you get n large, you get a certainly well ordered system here. Now it's 7. Just changing. We don't know why. We just observe it. 0.35. Sorry, now this is I've taken tau to be 50 and now changing the kappa, and you can see how the changes for different kappas are tau equal to 50. The area of which the transition is shrinking, and you see all these different situations. So that's what. So now to revisit what Djokovic did. So this one on the top left here is the original. And if you start increasing the n, you can see definitely a more coherent structure appearing as you increase n. And you see the period here where this is sevens, and the period here that these are only fours. These are Saint Charles. But again, the top left is what they originally had. And you can see coming out. Again, this is now becoming more as you increase. As you increase as well, so you get a patterning here coming as well as one here. In all these different areas where you're getting these different if I go to tomorrow, I originally started at 100, I showed the 250. This is now 2,500. And you can see that they're more much more exotic kind of pictures than what you originally had. And you told me now not in threes anymore. Except this one does still appear to be as threes. The one is through here. And that's when taking it to 5,000. So now let's look at the second case. So we've got kappa between 0 and a quarter. And so now I'm going to let beta 2n be u, beta 2n plus 1 be v. And I get this system here. And then just letting u be xi minus eta and v be xi plus eta, I can get a cubic for xi. And I can explicitly solve what eta is. And if you plot what those actually are, these are the shapes you get for different kappas of where what these actually are. Now, you can do some more analysis on them to work out explicitly where the critical points are when you've got an infinite derivative. And you can also show that they're actually going to get together eventually when it's capitals minus 2/3. So, as we've sort of seen earlier, these give you, if you just see the relatively small values of tau, you can see these, they're coming as a threefold sampling. The dashed lines are the solutions of the U and the V plots as well. Again, what happens if I take the parameter tau to be much larger? Then again, you get lots of different regions. For example, here, what causes periodicity of different amounts becoming in different parts, and they appear as you increase the tau. And this is if capitals are 6, a similar kind of thing here, but it's just different numbers in the quasi-periodicity. And here I've just kept, I'm going to now capture the third one, capitals name. And if you go back to Son and Child, you have one of this in this particular case. And I've done things slightly differently here as well in the plotting, in that on the bottom and the axis, instead of writing n, this is n of a capital N. So then you can see that you're going to give the same picture, but what you see here is that the vertical axis is always the same. And the point at which they sort of all join together is approximately the same value, all different cases. So now, what happens if kappa equals a quarter? Remember, this is the case I can solve it in terms of modified Bessel functions. But what happens here is that you put the three together, you find that the beta 3n is in here, and the beta 3n plus 1 and beta 3n plus 2 are almost on the same line here. You can actually show that they're not exactly, but the one's above it and one's below it, but that is what you can actually show. There's two branches. So again, you can analyze what these actually are. You now let beta 3n be U, beta 3n plus minus 1 be V, and put them into this. And so you now get this system here for U and V. And you can find, explicitly work out what the cubics for U and for V actually are. And if you set beta n to be beta for all n, you also get another cubic. And so I've plotted the three cubics here. The bits in the solid line are the bits that you will see are going to appear in the next plots. And the dashed line is the other parts of the cubic. So what you actually see is that the beta 3n follows the blue cubic almost and then just jumps onto the black. And the beta 3n plus 1 and beta 3n plus 2 follow the red cubic and then go onto the black. So it's very similar to what happened in the original quartic and sextic cases. If you take capital less than 0, or less or equal to 0, and then it's 0, you get this, and just as you decrease kappa, this transition period just starts decreasing until by kappa equal to minus 2/3, it's disappeared. And then otherwise, it just simply goes back to the division ones we had. Well, the ends here are particularly large. This is 275. So finally, I want to mention this Volterra lattice hierarchy. I'm not going to give it, basically, it's a hierarchy of equations related to the beta ends. And you can get them. The first one is just beta n. The second one is in terms of beta, is essentially quadratic, and the third one is cubic. The discrete equation satisfies, it's written in terms of Vn6, Vn4, and Vn2. And the we've known that the beta n satisfy two difference equations, and these are the first two members of the volatile lattice hierarchy. So what happens when I actually plot them for the different Vn? So Vn2 is going to be just a beta. This is what you get. You get effectively the same pattern for the different members of the hierarchy. It's almost exactly the same. The scales on the left change considerably, but otherwise, those are for three different kappas bigger than a quarter. If you take kappa less than a quarter, again, it's the same idea. You do the exact, essentially the same pattern exists for all of them, all three of the first three members of the hierarchy. So that's it. There's references, and that's it in my talk. Thank you.
This, so when you say that these patterns are identical for different hierarchies, you mean the beta and you construct the system of time?
Yeah, well, I mean, you're taking these by, I know what all the beta ends are, so therefore I then can construct this from all the beta ends. I can construct this one.
Yeah.
Because you showed for the first three, it must be true for all of them because of that recurrence relation.
Yes, eventually. I mean, it's a nice proof. Yes. So that's how they're done.
No, in general, in this first equation you wrote at the beginning, where you used to classify the weights. What is the meaning of this equation? Why the weights should satisfy them?
Well, it's been noted that in the classical orthogonal polynomials, they satisfy this equation here, that Pearson equation. It's just been noted that. And then it was seen that, and that the coefficients in the Pearson equation were actually the coefficients coming from the differential equation. And so that's a. I'll have to look what a reference is to that. I mean, it's just been known for quite a long time that you, from the differential equation, you can get this relationship between. So it would be known, I mean, if you take the differential equation for the Hermitian polynomial, that's the coefficient of the second derivative, that's the coefficient of the first. And so on. So no. So it had been observed that this was actually the case. And it just simply that it was then noted that for these others it didn't happen, and these, well, it didn't. And also these are not the. You can write down second order differential equations for the associated orthogonal polynomials, but these are far more complicated. They don't just involve them. I don't. I would probably be able to answer you better on this thing.
Any question? Anything wrong with that?
May I have a question? Can you please show the third order linear for the E? So what is tau there? It's a parameter
Tau is a parameter, rho is a parameter.
and rho is a parameter.
If tau is equal to 0, I can solve it.
So if you do something like Laplace transform or inverse Laplace transform or something, this 1 power of t goes into differentiation.
Yeah, I've tried that, it doesn't work.
I'm curious why.
I can't, I just remember, you just simply get to almost back to where you were, that you just cannot, I mean, Alexander, it's also suggested it should be easily done using the plus transform, so I did think of that, I did try it. I just can't, I have tried it several times, thinking I've made a mistake, but not been able to resolve it.
Okay, in my simple mind, the differentiation goes into multiplication of dual variable and multiplication by t goes into differentiation. So you get the first order. It looks like yes. Well, so
Again, it depends a little bit what you mean by solving, right? Because you will get an integral representation.
I have it for representation,
okay.
that isn't it, I mean,
Well, yeah,
I have this as an initial representation. So I can get lots of information from it. It's not completely wasted, but I just don't have we just don't have an expression in terms of what I know as known functions.
But those are hypergeometric, right? Generally.
Well, we can write down as, I can write down a series, I can write down as a solution in terms of infinite series of high geometric.
Yeah, but that's all coming from.
Yes,
Yeah.
Because basically what you can do there is, I know what it is if tau equals naught. I then just simply replace that by an exponential and then sum them all up.
Yeah, linear one always you can do the series.
If I can do this as a series solution, I just can't get as,
I'm curious, you say it's generalized hypergeometric function.
it's, well, because the case when tau equals 0, I can solve in terms of 1f2s. If I replace that by a series, I then simply just get the moments related from the sextic problem, and therefore I can actually get, but there's an infinite number of them because they're expanding out the exponential gives you an infinite series.
But somehow you say it's generalized hypergeometric function are related to modified Wesson, right?
No, that's a different scenario. If I replace t by kappa tau, then I can get modified. It's a subtle change. So I think, yes, it's quite subtle. I didn't expect to get modified better. It was just.
So you can get a representation in terms of a series, but you don't know about the convergence. You can't, in general, not in the particular cases.
I think I would guess they're going to be convergent.
It's a linear equation, right? So any solution has an infinite range for convergence because there's no singular point.
Yeah, of course.
I mean, I haven't checked it, but I mean, I do expect it's going to be.
Yeah, of course. Okay, that's like Marcos said, yeah. You have to check the singularity.
It's three, so there's no singular point. There's no singular point. Exactly.
Because there was singular point.
It's very bad.
It's not constant efficiency, yeah.
No, it's not. No, it's not constant efficiency.
But the same logic, then you would have no singular points and you have the geometric equation. That's not logical. No. It's the geometric has singular points. And it's not the reason it's gonna have something but in because just the infinity. Well,
But that's just not the regular single, right? Exponential time.
But I guess the issue is what is better for the numerical computation than the integral representation that we already have. Right?
Yeah.
Well, that is generous. Right, at least that's me hypergeometric, doesn't mean.
So it's
Not regular
complicated.
single.
So it's complicated.
The confidence, exactly.
So if I may interject this, so the main use of equation one is not so much because it's an equation, it's just it gives you a linear recurrence relation between the moments. So you just need the first three moments of the level 1, 2, the initial condition, and the others is just algebraic.
Yeah, you can define, yeah. There are no more questions or comments. Nice to see the linear equations warm our hearts. Okay, let's thank Peter again